Hi everyone, my name is Felipe Guajardo, this is Alex George, Dave Ducazi, our team is Def Motors, and today we're going to be talking to you about the race engine optimization project. Our main objective in this project is to modify an engine to better perform under the FSAE operating conditions. The Formula SAE competition is hosted and organized by the Society of Automotive Engineers. It is an international competition in which undergraduate and graduate students from universities around the world design, construct, and race open-wheel Formula race cars. These cars are subject to a stringent set of regulations which are stipulated in the Formula SAE competition handbook. There are a whole lot of regulations in the Formula SAE competition, but the ones most important to us in this project concern the engine. For example, all air has to go through a 20mm restrictor plate. The engine displacement cannot be more than 610 cc, and if you'd like, you can use 100 octane fuel.
Now, the way that we decided that we wanted to go ahead and meet these challenges is that we're going to take the engine from a Honda CB550 motorcycle. And we were going to raise its compression ratio up to better take advantage of that 100 octane fuel that we're allowed to use. Now, the reason we want to do that is because by having a higher compression ratio, you can have a more efficient combustion process going on inside your engine, and in that way you can extract more power from the fuel and air that you can get into the engine, rather than trying to expend more and more energy to force more air through that restrictor plate that you have to have. Now, the methodology for doing this is going to be that we would try to get our compression ratio up from the stock value of around 9 to 1 to a more appropriate for 100 octane fuel, 13.5 to 1. And the method to do that was to get the crankshaft from a Honda CB650 motorcycle. One of the primary reasons we chose the CB550 in the first place is that many of the engine components from Honda's CB family of engines are interchangeable with one another, and we could get that crankshaft to fit into the 550 block with no modifications. From there, we would have to get some custom light connecting rods to fine-tune that compression ratio to exactly the point where we want it to be, and to maintain piston valve clearances and not have any damage or explosions. So after an exhaustive search, we finally located and purchased a CB550 that had no problems, and it was running properly, and everything was great for about a week, and then we had a lot of problems. And every time we fixed one, we uncovered another one because we're working with a 30-year-old bike here. But okay, I'm not going to go into all the details about what those problems were, but what you need to take away is that most of them concern the fuel system and the carburetors, and ultimately we decided to discard those carburetors and just select a new carburetor that would be more appropriate for the reduced airflow requirements of the engine once we had that restrictor plate in place anyway. Now, once we made that decision, we had to develop an intake manifold that would distribute the fuel mixture to the different cylinders, because now we only had one carburetor when the original engine had 4 individual ones, one for each cylinder. Now, this design is loosely based on manifold types that you'll see in the industry. Commonly on 4-cylinder engines, you'll see this large chamber with individual intake runners going off to the cylinders. But our primary concern here was speed and ease of fabrication. We wanted to be quick and easy to fabricate because we thought this would just be a pit stop on the way to the rest of our project before we started making our modifications. And so it was designed to be quick and easy to fabricate. It was quick and easy to fabricate, and once it was quickly and easily fabricated, we drove up to Dania Beach and created a workshop, and we dynoed our bike, and this is what we got. Obviously, this is a mess. This would generally be considered to be a completely unusable engine. Obviously, this is a big setback for us. What we did is we sat back and we racked our brains for a while, and we talked with some professional engine builders at the creative workshop itself for some advice, and we determined that most likely the cause behind all these problems is the crude nature of this part. So we went home and we fired up SolidWorks and decided to run some simulations on this design. Now, obviously, this probably should have been done ahead of time, but hindsight is 20/20, right? So, as you can see here, this is just as much of a mess as you saw on the previous slide. Although you do see this type of design commonly used in production engines, if you were to run the simulation without the 20mm restrictor right here in place, the restrictor is integral to this design, by the way, this is a 20mm opening, you would see clear, relatively laminar flow profiles inside this chamber. Because you have this restrictor in place, your intake velocity right here, it's not on here, but on an unrestricted engine, it would be something like, I think, 30 meters per second. On this engine, it's 120. It's so fast and there's so much velocity, you get all this turbulence, which is causing all the problems we're having up to that point. So at that point, we made the decision that if we can't reliably distribute quality fuel mixture to our cylinders, we can't begin improving our combustion conditions. So we would have to alter the scale of this project. And the way we changed it, we decided that rather than modifying our mechanical compression ratio, we were going to develop an induction system that could better manage this high velocity airflow. This is the first attempt at finding something for that purpose. This is an intake manifold designed, it's based on a dual plane design, and the convention behind that design is that you're trying to maintain as close to equal length intake runners to your different cylinders as possible. And the conventional wisdom there is that by doing that, you can get equal amounts and qualities of fuel mixture to your different cylinders. And although you will see similar logic in manifolds designed for production engines all the time, once you put the restrictor on it, as we did for the simulation, we have almost all the same problems that we had with this design in the first place. And so we discarded this one and we moved on.
So with our second design, we tried to reduce that intake airflow speed. We inserted a hemispherical section in the beginning to kill that air velocity and then work from there into the runners. This did work in helping us get a more laminar flow in the outer runners, as you can see here, but it had some serious issues. When the air is hitting the wall, similar as in our first design, it caused a lot of back pressure and a lot of turbulence. This also led to an uneven distribution of air. This is a density simulation, by the way. This led to an uneven distribution of air into the runners and then eventually into the cylinders, which translates into a power loss. So we went with this design. Now over here, with this design, you'll see that we obviously went away from the spherical entrance into the manifold, and we tried to clear up the intersection for all four runners, an issue that we had in the first design. I didn't realize you. That's fine. So we cleared up the intersection between all four runners. Right over here. Now, this helped out dramatically in clearing up our flow and making it a little more even. We still had a little bit of turbulence right here in the beginning and going down the inner runners. And we still couldn't get the flow to be completely even among all four cylinders, or all four runners, which eventually leads to the cylinders. So we went with a different approach. Here we have a single plane manifold design, and we tried to, knowing that the restrictor was our issue and increasing the air velocity, we tried to design a venturi to deal with some of that, but we quickly realized that the space allotted in this Honda CD550 just wasn't enough to create a big enough venturi to deal with that. So the one we made basically didn't have much of an effect. And as you'll see here, what's happening is the inertia in the air actually drives the air into the inner two cylinders, and it has to come back out of the inner two cylinders to go to the outer runners. Sorry, inner runners, and then it has to come back out to go to the outer runners. Now, with this single plane design, we actually did improve our flow distribution quite a bit, but still we wanted to improve upon this.
So by the time we got to the fifth iteration of our design, we had determined that obviously most of our problems are stemming from having that high velocity jet of air coming into a point where we're trying to divide the flow in four directions at once. That's very efficient. So going forward, we decided to design this one to make sure that at any place where we're dividing the flow, we're only going in two directions rather than four at once. And we like this a lot. Obviously, you can tell just from looking at this flow plot how much better this works than anything we had done so far. So since we like this so much, we went ahead and we tentatively selected it, but we wanted to make sure that this is just the first foray into that idea of 2 into 4. So we wanted to see if we could make any further improvements, and these are the results of that. The idea with these two is that while having that 1 into 2 into 4 design, we would minimize the direction change for either the inner two or the outer two runners and see if we can get a better balance between the different cylinders. But running the analysis on it, it was causing more harm than good, and so we threw these out and we went back to the fifth design for our final.
So here is our rendered version of our final design. And all of the previous simulations that we ran it at 75 CFM, which corresponds to the engine speed at which the unmodified engine runs at peak power. Because the engine will not run at peak power for the majority of the time, we decided to further test this manifold throughout the whole range using 25, 50, and 75 CFM flow rates. So as you can see here, we have the 25 CFM simulation. We have laminar flow and good even flow distributions on the forerunners. For 50 CFM simulation, we have the same characteristics stay true and a good and no notable difference as well. And finally, for 75 CFM, as you've seen before on the previous slides, and you can see the good laminar flow and good even flow distributions on all the forerunners as well. Since we are Mythbuster fans, we wanted to push this manifold to the next level. So we made a 100 CFM simulation. As you can see, the flow characteristics start breaking down. We're having boundary layer separations over here, and as well as uneven flow distributions on the forerunners. Thankfully, this simulation was done at 100 CFM, which corresponds to about 12,500 RPM, which is far beyond the high speed this engine will ever run.
So here behind me and now in front of you, you have our original and final designs. In the next couple slides, we recorded our initial dyno test and our final dyno test. I'd like you to pay close attention to the sound of the engine as it runs through the pool. Even if we didn't show you the results, you'd easily be able to tell the improvement that this manifold makes, just the sound of the engine. Here's the first one. So as you can tell, in that higher RPM range, it almost sounds like it has a limiter. The whole system starts to break down. So now let me show you our final pull. Much cleaner. So just as a recap, let me go ahead and show you our first dyno pull again. We can call this a dyno pool. And then now our final results. Besides the fact that this is actually recognizable as a power curve now, you'll see that we greatly increased our average power, even though we weren't able to increase our peak power. Now, with the settings that we had on the carburetor for the initial test, it was actually running too lean. And so down here you'll see the air-fuel mixture. With the same settings on the new manifold, it actually right about 5,000 RPMs, it runs too lean. Now this is something too rich. Sorry. It actually runs too rich. This is something that's easily adjustable, and it would increase our peak power output. However, we just didn't have the tools on hand during the dyno pool to do so. So we've talked about how the design of the manifold and how we made the original one specifically with ease of fabrication in mind. Now, when we went and redesigned it and we're going for performance, as a consequence, ease of design wasn't exactly there. Manifolds are typically created in a cast, and nowadays you'll see it done in an injection mold. Neither of these solutions really were feasible for a senior group such as ours. So we had to think outside the box and come up with a new solution. At first, we had discounted 3D printing because it uses a lot of the processes, specifically FDM, uses PLA plastics and ABS plastics. Neither of which are known for doing well with gasoline. However, we did a little bit of research and spoke to some of the companies and found that this will actually work for our purposes. We tested it and it ran fine, and as you can see, it held up through our dyno tests.
So here is a quick cost analysis. We have the estimated cost and the actual cost. Some of the cost savings are that we were able to have a free dyno thanks to the creative workshop, and we were also able to contact a startup company, and we were able to get a very competitive price for the 3D printing manifold. Some of the additional costs that we had was that we had to buy the whole motorcycle instead of just the engine, so we could use it on the chassis dyno thanks to creative workshops. And for global learning, we were able to add some nonverbal signages on the engine, as well as our final version of the report will be translated into some various languages before the competition.
Yeah, and real quick, we just wanted to thank a few people who helped us out over the last year. Without them, this wouldn't have really been possible. First and foremost, Jason Winnick and John Dega at the Creative Workshop, who were the owner and the dynamometer technician respectively, who gave us a ton of help over this course of this last year. And then the Five family, who aren't here today, but they allowed us to use their garage to house the bike and work on it for the last few months, which is a massive help to us here in my backyard. And there's Javier and Tom, who both gave us some help with running our computer simulations when we got stuck. Rick Ziccarelli and Osvaldo Fernandez, who helped us to fabricate the original aluminum intake manifold. Didn't work that great, but we couldn't have got there without one. And finally, Brian Gleason, who gave us some help with a little bit of extra 3D printing at the end.
All right, so, and questions? Yes, Doug.
I've got two question pathways. First one is boundary conditions that you use in simulations. What were your basic boundary conditions?
We calculated the outlet volume flow based on the power output of the engine at peak, or the engine speed at peak output and the displacement. And we used that as the outlet boundary condition, and we used a pressure of ambient, 101.25 kilopascals at 300K at the inlet.
Okay, and was there any boundary conditions associated with the materials or the surfaces of the?
We knew that because like I said, we didn't go into the simulations until after the first run, so we kind of had an idea of some of the stresses going on. There's not, for the material, we weren't concerned, and definitely with the aluminum. With the plastic, like I said, with the ABS and PLA, we were a little bit concerned with the chemical resistance, and just because we're using plastic on a manifold, we did basic tests just to kind of see if it would hold up. Again, this is a prototype, so we really were just testing the flow characteristics. For long term, this would have to be cast out of another material.
I think you're talking about the surface finish of the material, right?
Right.
Oh, I apologize.
But also that did walk to a second path of questions, which was tied to structural stability of this. And what work did you do to?
Well, I'll talk about that in a second. But as far as the surface conditions, we didn't know exactly what the surface condition of the material would be until after it was printed, so we weren't able to simulate for that. But we did know that it would be the same regardless of what the different, the surface material would be different for whatever manifold we produce because they were all coming out of the same machine. So although they may have been, it might have affected it would have affected the results relative to each other as we're comparing our different designs, but it would have kept us off by a certain amount. As far as the structural rigidity, personally, I was really impressed with just how strong this was.
Well, I mean, that design is a little different than what you modeled.
Oh, right.
Because I see a structural member
this
down
was just
the
that
center.
once we contacted the company that was going to print it for us, their build area wasn't big enough to get this in one piece. So all we did was we chopped it in half and put a flange in the middle to glue it together. That's the only change. And in the end, it ended up being a good thing because that flange gives it a lot of structural rigidity since we're supporting this carburetor on the end of it.
Okay, I'd love to. But my last question, pathway, you told me as a proposed design, because right off your sheet here, increase the stroke and displacement, maximize compression ratio, and then compensate for loss of effective compression by restrictors. Can you walk through those and tell me how you achieved those goals?
We did not. Near the beginning of this semester, we altered the scope of the project because we had so many unexpected problems. At this point, it would have been beneficial to have a new poster at this point,
But it's basically, like you were saying,
Thank you.
that was our original goal, and we had to actually change the scope of our project, keeping the overall goal in mind, which was to improve the engine's performance for the Formula SAE competition. So this is actually, what we've done would be a first step in a multi-step process for this project. For the scope of the senior design course, we decided to keep the focus onto the manifold once we switch. As a full project, the next step would be then to to go back to what we were doing originally and increase the compression ratio and use 100 octane fuel.
Yeah, considering the time constraints, we're only now just getting to the point where we would start implementing those goals that we first talked about at the last time we talked to you. Unlimited time, those will be the next thing on our list, but here we are at graduation.
Thank you.
You hope, right?
Keyword.
Can I look at that?
So I guess I'll go. So I talked to you guys a little bit about this before, but can you talk a little bit about validation of your simulations? So you ran a bunch of different simulations, right? You got some flow characteristics based on those, but what does that mean in relation to the actual part that you have?
Okay, go ahead.
Obviously, that's something of a thin spot for us. What we really hoped to be able to do was to produce by 3D printing not just one manifold, but a whole bunch of different types, and did some tests running on a flow bench to confirm. And actually, I had been in talks with a contact, which was more like a contact of a contact who had a flow bench at the Robert Morgan Educational Center, where we might have been able to use that, but that fell through. We weren't able to use that piece of equipment. Unlimited, in a case of unlimited funding, we would have loved to do physical tests to confirm those tests. But as it stands, well, we have the evidence of the second dyno run. We can see the concrete performance gains there.
It's basically, the big point here is that our goal here is, or with the simulations rather, is more of an improvement. So we use the same process for all the different designs, and we saw the improvement in the designs using that same process. So it's more of a qualitative analysis.
Sure. Yeah. Okay. I mentioned this all to you before. The other thing you can do, just for other people who are here, also is use other results, right? So you're not the first people to ever run CFD simulations and then compare them to actual results somewhere. So you can try to use your simulation technique in order to compare with other people's actual flow bench results, right?
Right. And if we were to do this again, that would definitely
And
be
that
something we'd do.
costs $0 and it can be done in
literally less than a day. We would have,
Right.
like you said, that was mentioned to us a little bit earlier, but it was already towards the end of this project. We would have, knowing that ahead of time and doing this again, that would definitely be something we'd do a little bit more research, find a manifold that's been tested, and run it through our simulations at SolidWorks and see, with SolidWorks, and see the differences and see if SolidWorks does come up with the same results to validate our
Just because you get pathways along there doesn't mean that that means anything in relation to where you take it.
Right.
Now, like you said, you did see an improvement. I mean, no offense, but obviously you would see an improvement between the two different designs. The first design wasn't really meant to be any
Right.
sort of flow pathway. You have a big chamber, there's some air going in, and hopefully air comes out. But right.
That was actually
The second one, you're actually trying to guide that pathway.
Right. That's the thing we learned. We underestimated the effect of the restrictor, and this was a milestone in our actual goal, so we didn't pay too much attention to the manifold when we first made it. So when we switched it, obviously there was an improvement. We designed it now. This was just made to keep us going, and this manifold, the final one, was designed for its purpose.
Are there other ones like this already being used in other cars and things of that nature?
By this production process or that type of design?
This design and this production process.
The production.
Definitely not the production process. This is 3D printing is something that's only been really taken off in the last couple of years. And when we first actually started to consider 3D printing, we discounted it. We thought it would never, ever work. And it's been actually way better than our expectations. As far as that exact design, no, with cast intake manifolds, you may see something a little bit more complex, or in many cases less complex. You might be surprised just how similar to this. Certain ones you'll see. I was looking at the intake manifold on Ford's new, well not new, I guess it's like 2 years old, but the 5.0 Mustang engine they're using right now, it's got two of these.
Really?
One on each side. It's a box section, and they're longer intake runners. The actual intake manifold for the bike, we don't have it with us. There's a small neck going in, leading into each cylinder on the bike, which kind of meets up with it and extends this runner. But you have longer runners on a production engine where you have extra space to actually put it there and frame it away.
We got less than a minute for questions, and I have a final question. Were you through?
Yeah, I'm just going to stand for a second.
Okay. Your timeline that I'm looking at over there is obviously revised. Could
Yeah.
you speak to the revised timeline and the division of labor, and you have less than a minute to do that?
Actually, this is the result, the revised timeline here. All of us worked on everything together, but I mean, obviously there was different responsibilities for each team member. Alex, for example, was in charge of a lot of the technical difficulties we had with the bike. I helped him with it, but he was there more. He was in charge of it. You know, if he needed help with something, I was there to help him, but he was in charge of it. He was leading it. Whereas another example, this presentation, I was in charge of it. You know, so if we were working on something, you know, I said, okay, Felipe, you know, I need these pictures, I need this ready for this slide. So that's how it was divided. But again, like I said, you know, we all worked on everything together. I don't think there was anything that was individually done in this project.
Can I throw one more out? Can you go to your global learning slide? Global learning is what it is, but you're not really going to translate this into Italian, Spanish, and French before the competition, are you?
If this is going forward, I probably should have mentioned that with the manifold and the next process in this, that it's this ideally actually in real life scenario, we'd like to hand this off to another senior group and have them continue our work and maybe even do the work on this.
In Italy or here? In Italy or in the United States?
No, it would be here.
Okay.
I mean, the translations
No, I
would be
understand.
rough translations, run through probably a Google Translator or something.
Right. So that's all I'm saying.
for
There is a point to the global learning in the fact that people use cars all over the United States, all over the world.
Well,
Yeah, it has
there are
global
other
impacts.
to the
In one of the
Yeah.
earlier slides, we
Yeah.
talked about this international nature of this competition. I mean, the last time the team went to the competition, I think in the paddock next to them was a team from was it Germany or Italy.
It was Germany, yeah.
And that's one of the things about it. I mean,
So
obviously
write
we-
that on that slide. Don't write that you're going to translate the thing into Italian if you're not going to do it. We know you're not going to do that. Trust me. I know you're not going to. And if you do, it's one click on.
Yeah, I didn't mean to imply that this was
No,
going to be
no,
a
no,
professional
I-
translation. It's just literally,
That's
hey,
all I'm saying. So write that
know,
stuff. Just listen for a second. Okay?
Yeah.
Just write all of the other really key parts of your project that are international
Right.
on the global learning slide. Don't just write, we're going to translate our report into Italian. That's what I'm saying.
Okay.
All right.
I know you guys have global impact, but when we see this as, oh, we're just going to translate it into Italian, there's so much better things you can put on this slide than we're going to translate our manual into Italian. All right?
Okay, well, that's it. You guys are over time. Thank you very much. And